in this lecture, we will cover an introduction to chemistry. The periodic table is something that we are going to look at over and over for the next several discussions on chemistry. So we want to make sure that we know a couple general characteristics about the table itself. Since this is an anatomy and physiology course, we will be focusing mainly on elements a little higher up in the table itself. Carbon, nitrogen, oxygen. We'll hear about chlorine a few times, phosphorus a few times. You will hear a lot about sodium and potassium and calcium, and we'll talk about hydrogen here and there as well. Now, if this were a chemistry class instead of an A&P class, you would also spend a lot of time talking about these heavier elements. Okay? It's really just not a focus of A&P itself, because you tend to not find most of these heavier elements in the body. And since this is A&P and we focus on the body, we're just a little bit more selective about what we chat about with regards to the periodic table. Now, you will notice that the human body has 4 principal elements: oxygen, carbon, hydrogen, nitrogen. Okay? Oxygen makes up approximately 65% of your body weight. Everybody knows how important oxygen is. You know that if you have no oxygen, you will no longer be alive. That's how important it is. So hopefully it does not actually shock you that so much of your body weight is actually oxygen. It really is important, y'all. Carbon, hydrogen, and nitrogen. Right? You find quite a bit of each of these in your body as well. Carbon's about 18.6% by body weight. Hydrogen is 9.7%. Nitrogen is 3.2%-ish. Okay? You find carbons, hydrogens, nitrogens in the carbohydrates that we consume, the DNA that makes us who we are, things like that. So we do have a decent bit of all 4 of those, okay, oxygen being the greatest. Now, you'll notice that the next few, we didn't even put percentages until we get to iodine. And iodine, we're looking at 0.0002% of your body weight is iodine, okay, hardly any at all. But guess what happens if you have literally 0%? Things can go wrong. Okay, iodine actually plays a really important role in your endocrine system and your metabolism. So if you have none, you're going to have some problems. Okay, we might not need 65% every time, but if we have 0% of these at any time, that also causes major problems. Now, all of those elements that we just peeked at on the periodic table, they all have the same components. We have subatomic particles. We've got protons, neutrons, and electrons. Okay, many people have heard of these. Protons are positively charged subatomic particles. You'll notice in our little image, they've got a little plus sign. Okay. These live in the atomic nucleus, so the center of the atom. And they have neighbors, neutrons, which have no charge. They are neutral. Sometimes you will see the little symbol be an O. Okay, sometimes we'll show it as an O with a little line through it instead. Okay, again, either one of these just denotes no charge. These neutrons live in the atomic nucleus right next to the protons. Now, our third subatomic particle, these are called electrons. They have a negative charge to them. Okay, we've got a little negative sign or a little minus sign. You will notice that these electrons do not live in the nucleus. Instead, they surround the nucleus. They live in electron shells. Sometimes you will hear these termed orbitals. Either is correct. Now, if we are talking about atoms or elements, unless we specifically state otherwise, okay, we would always be talking about a neutral atom. Okay? And what do we mean by neutral? We mean that the number of protons equals the number of electrons. So the overall atom, okay, so the big picture, has no overall charge. Okay? Now notice, we said protons and electrons. We didn't even add in neutrons because neutrons have no charge. They don't help us balance out the overall charge one way or the other. Okay? Now, since our electrons live in shells. We have to talk about a couple rules about these shells. Okay? First rule is each electron shell can only hold so many electrons. Okay? So our innermost shell, the first shell that we would fill, can only hold 2 electrons. It's very small. It's like a little 2-seater convertible car. You can only fit 2 electrons. Okay? Now the next shell is a little bit bigger. It can hold up to 8 electrons. Okay? And they get bigger and bigger, and you can pack in more and more electrons. But rule number 2 is that regardless of how many shells you have, you always have to fill the smaller ones first. Okay, so you would fill this innermost shell with 2 electrons before you put any electrons in this second shell. Okay. Now, the outermost shell, the biggest shell, okay, we refer to that as your valence shell. The electrons inside would be your valence electrons. If your valence shell is full, then you are considered a stable atom. You would not want to make bonds. If your valence shell is not full, if you have room for just 1 electron or more, you would instead be a reactive atom. You would want to make bonds so you could fill your valence shell with additional electrons. Okay, so in this image we have 2 shells. Our inner one has 2, so that one's full. Our second one only has 4, but we just said that it could hold 8, so it's not full. Okay, so this atom is not stable. Okay, we can hold up to 4 more electrons, which means this atom can actually make up to 4 bonds. So it can acquire 4 more electrons to fill the valence and become stable. Okay. Now, let's make sure we really understand all the information that's presented to us in the periodic table. Okay. So we only took a quick peek. There are a couple of things that you are going to notice. And every periodic table is written just a little differently. So you'll notice in this example we've got not 1 but 2 numbers. If we go back to the beginning, okay, this one only showed 1 number. Okay, so this is much more basic of a periodic table. Okay. We do want to be familiar with both numbers. Okay. So let's talk about those 2 numbers. The top number is called your atomic number. Okay, your atomic number tells you how many protons you have in a neutral atom. Okay, so if we're talking about good old carbon, okay, carbon has an atomic number of 6. Every single carbon atom on the planet will have 6 protons. Okay, the elemental symbol, chemical symbol, and the element name, those are fairly self-explanatory. Okay. There's really no need to try to memorize any of these. You will have full access to a periodic table on your exams. Okay. We just want to make sure you understand what these mean. Now, this bottom number, okay, as you can see, this is your atomic mass. Okay, so here's what your atomic mass is good for. Your atomic, your atomic mass is your protons and your neutrons. Okay, so if we go back to our little picture that we just looked at, okay, we've got our protons and our neutrons in our atomic nucleus. Okay, all of these have mass. Okay, and that mass is equal to 1. So 1 proton has 1 mass unit. 1 neutron has 1 mass unit. Okay, so we always use whole numbers, so we would do good rounding. So this would round up to 12. Okay, if we say the entire carbon atom has a weight of 12 mass units, and we know that 6 of those mass units are coming from protons, we can do a little bit of math. We can do a little bit of subtraction. We can subtract the atomic mass, or the atomic number from the atomic mass, excuse me, and that will give us how many protons that we have. Okay? Atomic number from atomic mass gives us neutrons, excuse me. Okay, we are new protons. Okay? So 12 minus 6 protons would give us also 6 neutrons. Okay? Now, there are rules. There's always rules, y'all. Okay. First of all, don't forget to use whole numbers. Okay. You can't have a piece of a proton or a neutron. Okay. You're not going to need decimal points. But our rule here is don't just assume. Okay. A lot of these that you're going to work with, the protons and the neutrons will be the same. That's true. Okay. But if you get too comfortable and you just assume, that's the one time that will give you an example where the protons and the neutrons aren't the same number. Okay? So just quickly always do your math. 6 minus 12 is 6 this time. Okay? Now, if we are talking about an electrically neutral atom, and again, we will be talking about those unless we specifically say, hey, this one's different. Okay? So since we have not said this is not electrically neutral, we're going to go with it is. You know that if it is neutral, then the number of protons, or 6, would also equal the number of electrons. Okay, so this carbon would end up having 6 protons, 6 neutrons, and 6 electrons. Coincidentally, that would be this image that we just looked at. 6 protons, 6 neutrons, and 6 electrons. So this is what carbon-12 looks like. Okay. Now, I know that was a lot. We're going to do a little bit of practice. Okay. I want you to take everything you learned in the last couple slides. Okay. Go back and re-listen if you need to. Make sure you got it down. I want you to take these 4 examples, and I want you to draw what you think these would look like. So I want you to take these numbers, and I want you to draw this type of picture. Okay, for all 4 of those. So go ahead and pause your video, do your drawings. When you have finished your drawings, restart your video and check your work. Okay, don't just skip ahead and just draw down what I've already done. Okay, don't just write down the answers. You know you're not going to learn that way. So go ahead and pause your video. When you're ready, restart. Okay, now let's check our work. So here we go. Atom A, 8 protons, 8 electrons, 9 neutrons. Okay. If you count really closely, because some of these are hard to see, I had to kind of squish them in. There's a lot of overlap. Some of them might be a little harder to count than others. But there should be 8 pluses. There should be 9 little neutrals. Okay, all in the atomic nucleus. We also have 8 electrons that need to go in orbitals. So we have 1, 2 electrons in the smallest shell, which would leave us 6, 1, 2, 3, 4, 5, 6 electrons to go in that second shell. Okay. Alright, atom B, 14 protons, 15 neutrons in our atomic nucleus. Again, some of these little pluses might be a little hard to see, but I pinky promise, I think I counted right. Now we've got 14 electrons to deal with. We've got 1, 2 in our first shell. We said the second shell can hold 8, so we should have 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we've gotten through 10. We should have 4 left. So we've got 1, 2, 3, 4 electrons in that final orbital, or that valence shell. Atom C, we've got 13 protons and 12 neutrons in our atomic nucleus. Okay. Now we've got 13 electrons to arrange. We've still got 2 in that first shell. We should have 8 in the second shell. That's 10 so far. That would leave us with 3. 1, 2, 3 in that last orbital. And then last but not least, the 6, 6, and 6, that carbon that we've already seen. Okay, 6 protons, 6 neutrons, and then 2 electrons in shell number 1. That leaves us 4 electrons in our valence shell. Okay. If your pictures do not look like my pictures, please don't hesitate. Go back through this video once more, twice more, whatever you need. Okay. Please make sure you understand how to draw these pictures. Alright, so how do we tell if an atom is stable, okay, or if it's reactive? Another name for stable is inert. So just in case you ever see that word anywhere, stable and inert mean the same thing. It basically means that the atom would not want to make bonds. Okay, if it is reactive, it would want to make bonds. It's all about the outermost orbital. We called it that valence shell. Okay, if that valence shell is full, then our atom is stable and it would have no reason to make bonds. The whole point of making bonds is to fill the valence shell. So our carbon example, we had 4 electrons in the valence. We said the second orbital can hold up to 8, so we have room for 4 more electrons. That carbon atom would be able to make up to 4 more bonds to get those 4 additional electrons to fill its valence shell. If it does in fact get those 4 additional electrons it's looking for, it would then become a stable atom and would not want to make bonds with anyone else. Now, another reason that we don't want you always assuming that protons and neutrons are always the same number is because they genuinely aren't always the same number. Okay? Because of the existence of isotopes. Okay? Isotopes are basically different versions of the same element. So, for example, we have carbon 12, carbon 13, and carbon 14. Okay? Now, we've already worked with carbon several times. Okay, we know that we should have 6 protons, 6 neutrons, 6 electrons. Okay? Well, there are different versions of carbon. Okay? When we have our 6 pluses, our 6 neutrals, and our 6 minuses, that is carbon 12. Okay? This 12 refers to the mass number. Okay? We also have carbon 13 and we have carbon 14. Okay? So carbon 13 and carbon 14 are heavier than carbon 12. Okay? So where does that heft come from? Where does that extra mass come from? It comes from neutrons, from extra neutrons. Okay? So if we are talking about carbon, it doesn't matter which carbon, 12, 13, 14, doesn't matter. If it's carbon, it has 6 protons. That's literally what makes it carbon, is those 6 protons. Okay? If these numbers, okay, the 12, 13, 14, if that's our mass number, and we know that each one of these has 6 protons, and we've already said that electrons don't have any mass, okay, then the extra numbers are still your neutrons. Remember, we'll go back a couple slides. We said we could do our math. Okay, we said we could subtract the atomic number from the atomic mass to get the number of neutrons, right? So, if we do our math, okay, our carbon that we've been talking about, we had 6 protons, so 12 minus 6 was also 6 neutrons. Carbon 13, however, if we take 13 mass units, and we subtract our 6 protons, that would actually leave us 7 neutrons. And carbon 14, we would have 14 mass units total, 6 of those coming from those protons, so that would leave us 8 neutrons. Okay. So again, these are all carbon, just a little bit different of a variety. Okay, we've got different properties, different abilities of some of these carbon isotopes. Okay. But they're all still carbon. But again, these different mass numbers are exactly why we cannot just assume that protons and neutrons are always the same number. We always just have to double check by subtracting protons from mass. And that concludes our